Welcome to the AWS for AI podcast.
Welcome to AWS for AI, the podcast where we explore cutting-edge AI solutions and the innovators behind them. I'm your host, Hamza Mimi, AWS Solutions Architect. And today we are diving deep into the fascinating world of causal AI and its far-reaching implications across various fields. I'm honored to welcome our distinguished guest, Professor Kun Zhang. Professor Zhang is the Acting Department Chair and Director of the Center for Integrative Artificial Intelligence at Mohammed bin Zayed University for AI, where he also serves as a visiting professor for machine learning. Professor Zhang is also a professor in the Carnegie Mellon University Philosophy Department and an affiliate faculty member in the Machine Learning Department. He is widely recognized as one of the most cited researchers worldwide in the field of causal AI. With over 200 published papers, Professor Zhang's research interests span machine learning and artificial intelligence with a particular focus on causal discovery and inference, causal representation learning, and machine learning. His work aims to make causal learning and reasoning transparent in science, AI systems, and human society. Professor Zhang's expertise extends beyond theory as he applies his knowledge to diverse fields, including biology, neuroscience, computer vision, computational finance, and climate analysis. In this episode, we'll explore Professor Zhang's groundbreaking work in causal AI, its potential application, and how it's shaping the future of artificial intelligence and scientific research. Professor, it's great to have you with us today. Welcome to the show.
Thank you for having me. Hamza, very nice to meet you here.
Thank you. So before we get into the deep dive research, and we have a lot of things to discuss, can you tell us a bit about your personal story? You're born in China. You're a professor in Carnegie Mellon University. You came in from the US now to the UAE. What brought this interest in AI? And what's your personal story getting in where you are today?
Yes, wonderful. Yes, actually, during my PhD study, I really got interested in causality and machine learning. Why? Because I believe that we have to understand why things are happening, how to make a desired difference, and answer questions like what if something had been different, right? And at the same time, nowadays we have more and more data. So as a consequence, we can learn from data, which is essentially what machine learning aims to do. So I have been interested in causality and machine learning, and that's why. And then after my study, I was a researcher. I was in Germany for a couple of years. And then basically Carnegie Mellon is very well known for its contribution in the field of artificial intelligence. And specifically, I would say we have kind of pioneers in the field of causal discovery at Carnegie Mellon. Essentially, they made this field or this particular line of research possible. So that's why later I joined them to be a faculty member at Carnegie Mellon. And in the past years, we identified a unique opportunity right here in the UAE or Abu Dhabi. So, basically with this university, MBZUAI, we try to develop the right type of AI and try to transform the world in the right way with AI. That's why you can see the trajectory.
So you're really making the research universal in multiple countries, multiple teams. So you're part of the faculty members for Carnegie Mellon University and also now in Mohammed bin Zayed University for AI. Can you tell us a bit about what are the key research area you're working on in both universities, and where do you think the vision for both are actually going in the future?
Mm-hmm. Sure. Great question. So I personally care very much about why and what if questions. So from my perspective, even if you just want to make a prediction, whenever you deploy the system, then you can see the users and those who design the software, right, will basically see the difference, right? It has an impact on the users and on society. So that's why causality is really a fundamental problem. And of course, in many cases, say, we see the symptoms of Alzheimer's disease, but we don't know the true cause that can be easily changed. Otherwise, the situation will be totally different. Actually, you can see in history, whenever we can discover the new hidden causes of kind of important phenomena, or hidden laws like F equals ma or E equals mc squared, then the situation will become totally different. Humans will become more powerful and resourceful, and human society can become much better. So that's why I care very much about causality. Of course, at the same time, causality is a long-standing problem in philosophy and a lot of fields, right? And at the same time, you can see this is the right time to really go to next stage in causality research. Why? Because now we have basic tools and we have so much data so that we can really try to learn things from data. And that's why I could see the potential and opportunities. And I believe, I personally would like to make the causal process, including hidden things like a true cause of the disease like virus, right? Completely transparent to humans so that we can really just change what we should change in order to achieve a better future across many disciplines.
Yeah, the causality is a very deep human research field since Aristotle, where we had multiple citations from different philosophical figures across the history about cause and effects, which is still very, very relevant today. Before going maybe into the causal effect, can you talk about maybe Mohammed bin Zayed University for AI? This is a recent university that was created in Abu Dhabi, and it's very particular in the sense that's only focused for AI. Can you talk a bit about what's Mohammed bin Zayed University?
Yes, great. It's a university kind of that is completely unique, right? So it's the first university dedicated to AI all over the world. And you can see why it's a right time to have such an institution. A lot of universities have AI programs, right? Yeah. At the same time, you can see right now, in order to really educate qualified AI researchers, the paradigms or even the education model might be different from before. So at this university, you can see we aim to do say powerful and trustworthy AI, and we aim to really transform each discipline of science and each industry by making use of AI. So this is the right time to consider this problem and make a contribution. And at the same time, you can see the impact. And I believe almost all disciplines will become totally different in the very near future. As you can see from the Nobel Prize winners, right, who in physics, chemistry, and so on, you can see basically they try to discover the information behind the data, and then they can really make a lot of new things happen. So, and at the university, we aim to transform AI, so aim to address important problems across many disciplines. That's why we have departments, machine learning department, computer vision departments, natural language processing departments. But in addition, we are going to have decision science, biology, and public health, and so on. Because when you try to really deal with real problems, it's so important to really understand what the problems are and how to really find the best way to deal with the problem. That's why, so we are doing AI, but we are doing AI to really address real problems in human society.
Absolutely. And I can argue that all the physical world research and science is about finding causes to understand how the physical world basically behaves. Before going into the use cases, and I know you're working on different use cases, I want to go into the foundational concepts. And let's start with causal AI and causality. Can you explain in simple word what's causality and why it's important, and maybe causality in AI? What is it?
Wonderful, yes. In machine learning, right, or in recent development of machine learning, usually we care about the prediction. And very often we use a black box model, right, to make prediction into the future. That's already kind of powerful. However, clearly that's not what we want in many scenarios. For instance, for disease treatment, we care about not only the diagnosis given by AI, but also what kind of mutation cause the disease and how to treat the disease, right? So in order to answer this question, we have to understand the cause-effect relationship. right? For instance, if you consider rain and a wet ground, now you can see they are not symmetric. If you have a way to make it rain, then you can see with very high chance, then you see wet ground. But you can find a way to make the ground wet without really affecting rain at all. So now you can see the asymmetry relationship. If you want to change or achieve some consequence, and if you find some causes that can be easily changed, just go there, right? And this is how we can treat diseases. And this is also why nowadays you can see in biology, right, even in medical studies, we always care about cause-effect relations and how to find the right cause that can be changed. Yes. So this is what I mean by causality. You have to find the right thing or entity so that you can really change the target thing you want to change.
So causality is the search for the causes of the effects we are looking at, and there are multiple ways we can look at this, and I know you are very expert in this domain. But what's the difference? How can we recognize causality versus correlation versus association? As humans, we have developed that intuition of, okay, this is a cause, but we also still have that experimental way of getting the confirmation that this is actually the cause of something. How can we mathematically and based on the data differentiate between associations, correlations, and causality?
Wonderful question. This is the core problem in causality. Yes. So first of all, the classical view is that from only the observed data without doing any experiments, usually we cannot really identify causes, right? So because in the data, you can only see say correlation or dependence. But if you really want to find causality, generally speaking, we can still do something. One typical way to discover cause-effect relations is to use interventions or randomized controlled experiments, right? For instance, we try to see whether this particular way of treatment is effective. What can we do? We just put people or patients into two groups, right? And suppose the two groups of patients have kind of almost the same features, meaning that they have the same distribution for all the features, and then for one group of the patients, we don't do anything. For the other, we just apply the treatment, and then we can compare. And if the consequence is very different, right, we know, oh, this treatment actually makes a difference, right? So very often we can do such experiments. For instance, if you try to see whether rain causes the wet ground or the other ground, then we can try to find a way to just change rain and see whether the chance of wet ground will be different, right? Clearly, generally speaking, that's the case. And then you can also find a way to change only the wet ground, and then whether it rains would be irrelevant, right? And in this case, you can see, I know rain causes the wet ground, but not the other ground. So this is the classic way to discover cause-effect relations. But this is almost too expensive, and sometimes it's impossible or it's unethical. For instance, right, if you try to see whether divorce has some effect on something, how can you really force people to divorce, right? Yeah. So that's why in the field of causal discovery, we try to just identify cause-effect relation and even hidden causes just from the data we can observe. So this field is particularly known as causal discovery. Yes.
So there are multiple ways, and it depends on the data we have, obviously, and how we will treat time series data, for example, is going to be different from like general data. Yeah. Because causes are generally happening before the effects, I guess. Yeah. But to go to the example of wet ground, it can happen from all different sources. So, and you mentioned some experimentation where we cannot actually do the experimentation. How can we mathematically, just based on data without doing the regular process of hypothesis, experimentation, manipulation, and getting the data, how can we just based on massive amounts of data get that intuition and discovery of cause?
Wonderful. So basically the principle is known as the fundamental principle is known as a kind of modularity property of a causal system. What does that mean? We have a system involving rain, wet ground, and so on, right? You can see all those things can be dependent, right, with high correlation. However, if we have the system in which rain causes wet ground, we know actually the system can be decomposed into irrelevant modules. One module or one process generates rain right there, and the other generates wet ground from rain right here. They are not related. The two things are not related. Although variables are related, now we can see we have very clearly defined modules involved in the whole process. And this is very natural. This is how we can do divide and conquer. And this is how we can build aircrafts. We divide the job into different modules. You take care of this part, I take care of a different part, and then align each part basically certified. Then we can put things together, right? And then we have the a good system, big system. Okay. So this is what I mean by modularity. Basically, all methods that can help us discover kind of causality or causal information from observational data are different kinds of instantiations of this property. We just try to see how to find a model behind the data that can satisfy the modularity property. So in other words, if rain causes wet ground, then when you first model rain and then model wet ground given rain, then the system is very simple. Otherwise, if you consider a problem in a different direction, the system would be very complex. So that's the basic idea. I know, yeah, this might be too technical. Essentially,
it's very interesting. So you're basically using the divide and conquer. Are you dividing also the features of the data you're having?
Yes. So usually we talk about the causal relation among the features, right?
Okay.
Of course, in many cases, it makes no sense to really talk about the causal relation among the features. Let's consider one problem, right? Suppose we try to see the personality, and then you can design questionnaires. Then we have so many answer scores, right, to the questions. Then, generally speaking, although the answer scores, right, are clearly related or correlated, there are no direct causal influence in between. Okay. Instead, generally speaking, they are caused by the underlying hidden mental conditions. So in this case, you want to analyze the dependency patterns of the measured variables, right, aiming to discover the hidden variables and the relations. Yes. And this is also kind of part of the problem of causal discovery or causal representation learning.
So that is a very interesting point where sometimes we don't have that cause in the data we have, and it's a hidden variable. Maybe it's a composition of different features that we do have. Are we able, using AI, to find those hidden variables, and how can we do that?
Wonderful. Yeah, that's a great question. The short answer is, in most cases, yes, and we aim to produce very reliable method to do so. Why? Because, scientific discovery is mainly about how to really understand the phenomena so that you can see what's going on behind the data, right? As I just mentioned, if you discover the hidden causes of what you observed, then you can try to find a way to measure the new things, and you can even try to manipulate them. Then you become more powerful, right? So that's exactly the progress you saw after, say, that discovered virus, right? If you know actually those diseases or those symptoms are caused by virus, and you try to understand how to manipulate the virus, then clearly you can treat the disease in different ways.
Yeah.
Yes. So right nowadays, I would say across many different settings or different problems, yes, we have specific methods which can directly recover such hidden causes and even the relations among the hidden causes. Like we have different mental conditions, right? We have different dimensions of the mental conditions, and the different dimensions may be related. For instance, right? If you talk about personality, probably the underlying dimension of personality known as, say, agreeableness would be a cause of extroversion. Right? So those relations among the latent variables or latent representation could also be discovered from the measured answer scores.
Okay. And so depending on the data and the use case we have, sometimes it's easier to get to that causality relationships. Are we able to quickly categorize these areas where it's feasible and the areas where we simply don't have the data?
Wonderful question. Wow, that's a really cutting edge question to ask. So I would say yes. Generally speaking, if you have enough data that are diverse enough to cover the system, then you can relatively easily discover the hidden variables and relations. But in some fields, in some particular domains, maybe you can only measure a very small number of different things. As a consequence, you don't have enough information to recover the whole picture. Then in that domain, it will be very hard to discover causal relations. For instance, we talk about psychometric studies, right? So we can measure so many variables. We can try to think of different conditions, and we design questionnaires, and we can measure so many things relevant to the mental condition. Yeah. Then this field is not difficult to really discover the underlying reasons of the answer scores and try to give some interpretation of the reasons. And in some other fields, for instance, even climate science, it might be pretty hard because usually we don't really measure too many things. And the system is very large, right? There could be a lot of kind of relations and hidden things. So it'd be pretty hard. We are doing research in this field, but compared to those, a number of healthcare problems, biology problems, I would say climate science is still a pretty particular domain that is very challenging.
So climate science and climate analysis is basically one of the largest domains where we have a lot of calculations, a lot of data, and it's hard to modelize everything. And there is also the butterfly effect and all sorts of effects that can go into play. Is it fair to say that it's depending on the size of our modelization of the problem that we are able to get the causality or not?
I would say, first of all, complexity could be one factor, but it may not be the crucial factor. The crucial factor is something related to the information you can measure versus how complex the problem is. So if the ratio of the information you can measure, right, to the complexity of the model is high, meaning that you have a lot of information, then it's easier to solve the problem from the causal perspective. However, in some other scenarios, although you measure so many things, the problem is so complex. As a consequence, you still don't have enough data or enough information to recover the complete picture behind the data.
Okay, so there is the computational power, the algorithms, and how we are actually treating this problem, and the complexity of the problem and the data we have.
Exactly.
And it's a combination of all of these three.
Exactly.
Okay. Maybe can you maybe speak about what are some of the ways we do the causal discovery? I know this is a fast research domain of yours, but just as a high level, how are we treating that data in order to define, let's say, for a basic example, where we are able to define that causality? What are the ways we are doing this?
Mm-hmm. Wonderful, yes. That's a technical question, but I'm very happy you asked the question. So it's not mysterious. So a classical way to discover causality is to make use of how variables or entities, right, or events are dependent on each other. Let me give one example. Suppose now we have, say, now we have two persons. Suppose we have the third one right here, right? So Hamza, whenever you do something, the third person may follow you with some probability, right? And similarly, if I do something, the third person right here may follow me with some probability. Now suppose there are no influence in between us. Now you can see clearly the causal relationship would be going from you and me to the third person, right? Yeah. Because both of us can affect the third person, yes, although we don't influence each other, right? Now we can see from data, we can easily discover this pattern. From data, you can see, since there are no relationship in between, our behavior would be independent, right? Would be independent. There are no dependence between us. But between you and the third person, and between me and the third person, there will be dependence. Okay. And then there's only one explanation in this case. Both of us would be the causes of the third person.
Okay. So we basically look at the data, define the features and variables that are independent and the ones that are dependent. And basically on that, we are able to start inferring the causality between the different variables.
Exactly. So it's basically the way to make use of dependence and conditional independence or independent patterns to infer the information causality. Exactly. That's a classical way. Modern ways make use of kind of more advanced machine learning settings and algorithms to discover deeper information. So for instance, even if you have only two things, two variables, say, suppose, let's consider you and me. Suppose whenever I do something with some probability, I follow it, but there's some noise, right? So I try to follow you, but there might be some noise. Then generally speaking, you can see the following phenomena. So when you try to explain my behavior from your perspective, right, by making use of your behavior, then the system is very simple. Why? You can first explain your behavior, and then when you try to explain my behavior, on top of your behavior, you just introduce some kind of independent factor you cannot control, right? Because I try to follow you, but there's some noise. However, you can show that generally speaking, if you try to explain your behavior by making use of my perspective, meaning that you consider you as the effect, while me as the cause, then the system would be, the mathematical model would be very complex. Generally speaking, you cannot just first explain my behavior and then explain your behavior by making use of my behavior and the independent noise. You cannot find the independent noise anymore. So it's a kind of asymmetry between the two variables, Hamza and Kun.
Absolutely.
Yeah.
I can see how that can be a very computationally hard problem to solve as well, because of finding the relationships, but also the ratio from signal to noise, and developing the highest, most performant algorithms in order to find that is basically a big domain of research. Now that we've talked about the causality and how to get to that, I want maybe to push on, okay, now we define that relationship. How can we make use of that relationship? And there are the applications, but from a theoretical perspective, maybe I can touch on the explainability in AI, and also maybe a little bit about the counterfactual reasoning. So maybe let's start with the explainability. How can we use the causality definition in order to have more explainable AI?
Wonderful. So there are different ways to think of explainability, right, in AI. Sometimes we just try to have a mathematical model. We just try to see how the input features affect the outcome, right? It's just a mathematical model. But very often times we try to use a causal model to explain it. We try to answer why questions. For instance, right, in AI diagnosis, maybe you want to see, why basically is the diagnosis result going this way, right? Why for this person, particular person, right, the diagnosis result is, say, is positive. You may want to answer this question.
Sometimes with similar symptoms as well.
Exactly.
Yeah.
In that case, you may want to see basically the effect of the disease. And then this is because when you do diagnosis, you try to find the relevant features, but you want to give a clear explanation so that the doctors can really see what's going on, right? So you may want to go to a particular region and say, right, this region basically has this function, and for this person, this region basically has some issue, right? So this right here, we try to explain or answer why question by making use of the underlying causal relations. So, right, we, and very often times we try to achieve explainability for the purpose of making a difference, right? This is basically a causal problem. So for instance, we try to say, why is this person so poor compared to other persons? And when you try to answer this question, automatically or very often times you try to see what this person could do in order to make a difference, right? So in this case, clearly you may want to make use of a causal model to explain why.
Okay, let's go back then to the counterfactual reasoning. Once we have that root cause that we have identified, we can infer other scenarios. Can you maybe explain what's counterfactual reasoning and how can we use that?
Wonderful. So basically, counterfactual reasoning is about imagination based on what you see. So from my perspective, counterfactual reasoning might be the best way to achieve personalization. So actually, it's a way to really make sure you can see the hidden information and make use of it. For instance, one kind of a couple, right, says, "Oh, you are unique to me." What does it mean? Basically, they can see the unique features or hidden features that others cannot see. And then they can understand each other very well across different scenarios, even if the scenarios are just imaginary, right? So basically, counterfactual question is about the following question. Say, today is not raining. What if it had rained today, right? What would have happened to me if it had rained today? Now you can see by doing this kind of question, we can try to reflect on what happened, what we did, and so on. And then, given that reflection, we know what we should do in the similar scenarios, right? And at the same time, counterfactual reasoning is very different from the traditional kind of prediction model involving a lot of features. Because in counterfactual reasoning, we have to see what happened and then infer the hidden thing. By the way, here, it's very interesting to see that actually in the world, there is no noise, right? If you have a causal model, say rain causes wet ground, we know relative to rain, there could be some noise in wet ground. Why? Because of a lot of other conditions. However, the noise is only the omitted factors you didn't measure. They are just regular factors, right? And as a consequence, with the counterfactual and a causal model, you can really try to infer the noise so that you can have a better understanding of the whole system to provide a more informative answer. So if you like, I can give another example. So for instance, suppose we know attendance is a cause of final grade, right? So this is the end of the semester, right? Students care about the final grade. So suppose attendance is a cause of final grade. Now suppose for me, particularly for me, my attendance is pretty poor and my final grade is very poor. You may want to see what would have happened to me if you had forced me to, say, attend more classes, right? In this case, you can see you have to try to see my hidden information from what you observed. For instance, you can just try to see that compared to other students, actually, other students who had similar attendance, my performance was relatively poor, meaning that maybe I don't pay attention even if I attend the classes, right? And this is the hidden feature. And then when you try to see the consequence of intervention, say forcing me to go to more classes, then you have to incorporate that part, right? That feature of this particular person. Then you can get a more informative answer.
That would be a very interesting model to have, actually. So, I can also imagine that this counterfactual reasoning can be used for emergency situations, for example,
Yes.
in order to infer the what if we handle this situation differently and then enhance our operational readiness for future situations and all sorts of applications. I want to go back to the explainability part and maybe talk a bit about the reasoning capabilities of large language models that we have today. And I know this is a field where we have different ways of doing the explainability bit, and causal AI is one of the major ones. How can we use causal AI in order to understand how large language models generate text?
That's a great question. So right now you can see a lot of systems, including ChatGPT, right, make use of autoregressive generation together with transformer architecture. So in some way, it's very powerful, right? Because you have a lot of data, you can really memorize so many patterns, dependency patterns. But on the other hand, you can see clear problems. We collected a lot of examples. So this kind of platform, like ChatGPT, can really make some naive mistakes. Why? So in some way, you can see there could be a big gap between our reasoning process and what language can do, right? Large language models are trained to try to mimic the human reasoning process. However, you can see that primarily, language is just a way or tool for communication instead of reasoning or thinking. There could be a big gap. And as a consequence, in some situations, you can see the result is very good, it's very convincing, but in some other scenarios, there could be very naive mistakes. I think you are aware of many, right, such examples. So from my perspective, the issue is, actually there are multiple issues. One of them is that large language models right now may not really have the right types of representations. For us, when we look at different things, we encode concepts, relation among the concepts, right? We make use of our understanding in terms of concepts and relations and logical implication and so on, right, to answer questions. But now, basically, large language models make use of dependence pattern or association of information without directly deriving such kind of concepts and relations and so on. As a consequence, sometimes some patterns would be completely lost. So you cannot really answer some particular type of questions. So, for instance, we make use of particular architecture or structure in the brain, right, in order to really encode the different kinds of information, including causal information, logical relationships, right, and so on. But for large models, there are no such ability. So, as a consequence, right now, with only text data as the input, I believe the power of large language models is kind of limited. So there could be multiple ways to go further, right? Essentially, I believe what we expect from large language models is something like to have a artificial brain, right? The large language model can really connect different kinds of input or different modalities, right? Including video data that we can see, pictures we can see, audio information we have access to, and the text and so on. And then at the same time, you may want to touch things and see the feedback. And then you really have the proper way to encode what's going on, right, in reality and how things are related. And then large language model can be much more reliable. But now I would say, given the gap between what language contains and what we expect in terms of the reasoning process, yes, there's a long way to go.
Okay. Do you think this will require a fundamental change in the transformer architecture and how we currently build large language models and foundational models, or it's a tweak to the existing architecture?
From my perspective, my own perspective, I believe, yes, we have to come up with a different way to represent the learned information inside the large language model. So, for instance, you may have some kind of transformer architecture, but somewhere you have to encode the, say, temporal information, concepts, relation among the concepts, causal implications, and so on. So, for instance, in our brain, right, we have neuron clusters, and we also encode, say, different concepts by making use of multiple neurons. And at the same time, we also have the connectivity, right, specific connectivity involving specific regions, right? Those things should be included in the large language models at some point.
I want also to spend some time speaking about some of the practical use cases, and you have focused on the real-world applications of causal AI. One of the papers that you published is about causal reasoning and persuasive dialogue, and how we can use the causality in order to understand the causes for a person to react a certain way, and in that particular paper to augment the donation amounts. How can you explain the use of causal AI in order to influence the dialogue and the exchange?
Wonderful. So now suppose there are two different salesmen, right? That try to sell something. One of them could be very convincing. The other may use the same way to deal with different people, right? And you can imagine how the outcome is. So what's the difference? Essentially, the first one, a very good one, is very good at discovering the hidden information of the particular, say, a customer, right? By making use of the interactions. For instance, right, very quickly the salesman may discover that, this person basically, say, is very considerate. And as a consequence, this customer may want to get something for his friends, right, or his kind of partner. So, and then such information you can see is hidden, right? It's not directly given. But once you discover such information, you can do something accordingly, right? And for the second one, although this person can make use of a lot of information, but the hidden information, the hidden personality, the hidden desire would still be hidden. You cannot really make use of it. That's why if you have a system that can really discover the hidden features like personality, desire, and intention, and so on, and then clearly can make use of it, right? We can understand each other, and we can try to do the right thing to satisfy each other.
So every interaction is basically a source for additional information that your model is able to capture and use causal AI in order to find causes that enhance
Exactly.
the response,
and to do something proper for this particular person, right?
to get a different way of behavior. This is also one of the application of counterfactual reasoning, I guess, right?
You're totally right. Yes.
Okay. So what if so basically in real time, the model would consider different versions of how they should address a certain customer and use the one that basically provides the best value for a specific feature.
Exactly.
Okay.
Yeah. Based on understanding, you can predict which one is really the kind of most effective one.
Brilliant.
Yes.
One of the other domains I know you're looking in is in education. Can you speak a bit about the work you're doing maybe with Ministry of Education here in UAE, and how can we use causal AI in education in general?
Wonderful. So I personally believe so in AI, there are not many problems we really we should address, right? So those domains include healthcare, education, and probably climate science. So in education, first of all, healthcare is very important because we can really make people live kind of more happily, right?
Yeah.
And at the same time, we care more about the next generation. That's why education might be even more important. And you can also see the issues with education right now. And first of all, you can really see a big difference between a talented and a devoted teacher, and a kind of mediocre teacher, right? So the first type of teachers would be able to really understand the hidden information of each student and do something accordingly in order to make a desired difference, so that each of the students can become different, right, in a better way, right? So, but for the second one, it's very hard, right? You may just want to do the same thing to different students, then some students may benefit from that, but some students can really get hurt. So that's why you can see with AI and the data, we can really discover this kind of personalized information and make use of it, so that all of them collectively will be better, and that each of them will be a better version. So that's our purpose. And there are different ways to achieve that, right? We just make use of all kinds of data we can observe and try to see the underlying reasons for different behavior. And then given that reason, there will be some suitable recommendation or intervention we can try to apply in order for this person to become different.
Okay. So in an ideal student experience, there will be some kind of assistant to the teacher where it will provide him with customization for each of the students, maybe in their homework, maybe in how they interact, and provide that customized learning path depending on different behaviors and different data from each of the students.
And even in terms of curriculum design, maybe you want to make it specific, or you want to make it personalized, because students learn things in very different ways.
We can even push this maybe to the students. Where are the areas of interest of the students? What kind of career path they can follow? But this also brings other questions about, should we use this for ethical reasons? So there is always that balance between we can provide a better experience for the people we interact with, but we can also use this technology in ways that the ultimate customer, the ultimate user, does not approve of. How do you have any specific thinking about this particular problem?
Wonderful. Yes, a great question. Before that, let me add one sentence to the previous one. So we are doing student-centric and also teacher-centric and school-centric and parent-centric kind of modules. Why? Because you can see clearly students should be the center, right, of education. At the same time, we should try to find a way so the teachers can be more sustainable, right, and that the school could allocate the resources in a better way, right, and so on. That's why we have different modules. And now come back to the question you just asked. I believe you are totally right. So it's a very hard question, and from my perspective, in order to do so, we have to make sure the system is, first of all, transparent, and second of all, certified. So certification is very important. You should make we use a fridge, we do cars, right, every day. You can see those things are clearly certified, right? And you can see the system is, although the system may not be completely transparent to you, you can trust it, right? Because the experts already did a lot of work in order to make things reliable in many ways. For AI systems, it's the same thing, right? And first of all, we can just try to, as you mentioned, right, explainability would be very important.
Yes.
We can make it transparent in terms of explanations. And second of all, the system should be, the information should be available at least to experts. And after that, the system should be certified so that we can see why this system is developed and deployed, who will benefit from it and why, and how, and whether some other people basically will have to sacrifice, right, for this reason, and so on. And then we can make the final decision or collective decision based on that.
I want also to touch on maybe other use cases. We talked about education. We talked also about climate analysis at some point. Finance is also a big topic of research of yours, and finance volatility and how you modelize the market is a big domain of research for everybody since forever. How do you think causal AI can support the research and have practical applications in finance?
Wonderful. So you asked about climate science and finance,
yes,
right? Maybe I can just say a few words about both of them. So in climate science, you can see we aim to understand why, say, that climate change phenomenon. And we aim to see whether we can do something to prevent the very poor phenomena, right, from happening. And we try to improve the situation and so on. That's why we have been trying to recover the underlying driving force of the change and see how the pattern, even the climate patterns, how the patterns actually changed in the past years, and how to locate the fundamental causes and how to understand them and how to find the best or possible ways to change them. So that's our final goal in climate science. So you can see why causality plays a very important role, because we try to really understand the fundamental causes of the change and give interpretation and find a way to make a difference.
And go into maybe the depth of specific features in the climate per region, per specific location maybe.
Yeah. And there are kind of global factors and also local factors. You are totally right.
Okay.
Yeah.
So understanding the cause and use that in order to infer what will be the implication in a local specific place, maybe in a particular feature, heat, humidity, whatever, moving forward.
Yes.
Okay.
And then you can, based on the understanding of the causes, you may want to find a way to do manipulation, right? For instance, if you see actually this cause is heavily related to, say, greenhouse gas, right? Then you can try to, you can try to find some way to reduce the emission of the.
So modelize depending on the trajectory and the greenhouse gas effects.
Exactly.
And maybe also depending on local adaptation
Yes.
scenarios where maybe you have mangrove being built. Does it have an effect on different areas?
Yes, exactly. And the kind of very tall buildings, essays, right, and so on. So there are many factors.
Brilliant.
And if you can quantify the effect of all those possible factors and finally we can just see what price we have to pay, right, to maintain good life. At the same time, we can really try to see what we can do, right, to make life not only happy but also sustainable.
Absolutely. Brilliant.
Yes.
Okay, let's go now to the finance part.
Yes.
So what are the applications that you are working on the finance world?
Right now, we are really working on kind of a trading system. So I would say at this moment, we haven't explicitly made use of causal AI, but you can already see the power of, I would say, even traditional AI, if you formulate the problem in the right way, right? And the key point is that follows finance or investment is not about prediction. In traditional investment, you try to find a kind of fixed model, right, that can make good prediction all the time. Then you try to make use of this model. However, in finance, we don't really care about the performance of a fixed model. As long as you can identify relatively rare, so let me say again, as long as you can identify the relatively rare opportunities where you can predict the future and the market changed a lot, then you can just make money, right? That's the fundamental, basically, idea. So the issue is how you can just identify those opportunities, right? Because in finance, things are heavily non-stationary. A lot of things change over time, right?
Yes.
And at the same time, from the causal perspective, we are also doing a project trying to really understand the driving force of the change. If you can identify the driving force and also make prediction in this way, and since most people don't really realize the existence of a particular hidden thing, while you can do it, then you can also find new opportunities, right, to make use of the predicted result.
So given the complexity of the system, it's not about predicting the causes of everything because we have a high volatility.
Exactly.
But just the ones that we have, we are able to identify those hidden features that we can predict in short term.
Yes.
To basically get some additional value out of it.
Wonderful. So if you compare the very experienced investor and kind of a new one, now you can see the very experienced one can detect and make use of many opportunities, right? But still, I don't think this investor will basically do trading all the time. Sometimes, right, the person may not be confident, right? You don't have to do anything. But for the new one, probably, yes, the person cannot really identify many opportunities in a reliable way, right? So basically, with the AI, we can really try to be a very smart investor who can identify as many opportunities as possible reliably.
Perfect. There is also, and maybe I want also to touch on another field very briefly. You spoke about the mental disorder and the applications in healthcare. How we detect ADHD, how we diagnose different effects and causes for a specific treatment. How do you see this moving forward as another way for us to detect, treat, and then have a better diagnosis for different illnesses?
Wonderful question. So you can see when we try to deal with mental conditions or kind of mental disorders, right? First of all, we have to understand the underlying difference across different subjects, different people, right? And we have to see the reasons. And this is basically a causal problem because we cannot directly identify the causes. We can only design, say, questionnaires and make use of rating scores provided by the kids or parents, right, or doctors. And that's provide a way to automatically look into the hidden world, right? You can try to see the reasons and different reasons. And then once you go to this step, you can try to see what would be the causes. And then based on understanding, you can try to design very safe therapeutics to make a difference. For instance, in one of the projects we did, we try to identify what type of game, digital game, would be very effective in order to change a particular dimension of the reasons behind ADHD. First of all, it's safe. And the second of all, you can see, for kids, right, playing a game for 20 minutes every day would be fine. But if the game is designed in a specific way, then the particular reason of ADHD can be different in a very natural way. So that's why understanding the underlying reasons and trying to figure out what kind of safe intervention could be used to change that reason would be so relevant and important.
It's brilliant. So beyond the diagnosis part, even the treatment part, we can actually experiment without impacting the patients.
Exactly.
And,
and you can do counterfactuals, right? Because now you can see once you have the causal model, basically the world is transparent, right? Even if those things never happened, you don't care. You can use the counterfactual reasoning to see the consequence and to the comparison, and finally you can find the optimal action.
Brilliant. Before we end, I want maybe to ask you two questions. One for the research world, and what do you think AI is going to look like in 5 years from now? And with that vision, what would you advise the current researchers working on different AI projects?
That's a great question, very broad.
Yeah.
And from my own perspective, I care very much about the impact of AI. The impact of AI should be transparent, but now I believe this kind of research is heavily lagged or even underexplored. So I believe we should care more about the impact of AI tools, and we should care more about the future of human society in terms of, say, confidence, right? Human confidence, intelligence, and independence, right? So in some way, right now, those factors are ignored in some way. So I would say when we do AI, even when we try to formulate AI problems, probably in the future, we should try to see the consequence of this particular development in the first place, right? Let's talk about the recommender systems. Right? Recommender systems are so good because they can make our lives much easier, right? You can easily see what you want. At the same time, you can see a clear consequence of traditional recommender systems. Essentially, first of all, it could be just a way to repeat history, right? And the second of all, you can see it might be a way to just get addicted to what you like. And if we are addicted to what we liked, then as a consequence, our world will essentially be smaller. And it's more difficult for us to really understand the different persons, right? And to make the society more harmonic. So that's a very poor effect of recommender systems. Right now, I would say personalization is almost everywhere. So, but some kind of personalization will basically try to satisfy the users in an immediate way. I don't think that's always good. And at the same time, without personalization, usually you can see AI system will provide the same answer to different people. But we know people are different, right? They are inherently different. This kind of feedback can make the society less diverse. So I was talking about the relatively unhappy consequences of AI, but those problems can be addressed. If we care more about humanity and the future, those questions will be answered in the relatively near future. And then when we develop new tools, we can try to pay attention to the consequences. And finally, I believe we can achieve not only convenience and safety, but also sustainability, right? And even better individuals.
Very, very optimistic view for the future. Final question is, you work with AWS, and some of your students are building AI models on AWS. What's your advice for people, or maybe feedback that you can share about the good, the bad, and the ugly? What some of the things that you've seen work and how the cloud actually help your students and researchers in general build better models?
Oh, wonderful question. So my students and our researchers make use of AWS almost all the time. So it's great because it's broadly reachable to researchers from very different fields, especially to those who work on interdisciplinary problems, right? They can easily work together via AWS. And at the same time, it provides very nice storage functions and it even provides a kind of web services and so on. So in this way, I think it's really kind of valuable. And at the same time, I would say when we use AWS services, right, it's always good to have a concrete plan, right, regarding how to use it. We don't have to waste the resources.
Yes.
And at the same time, I believe AWS can really facilitate big projects to address real problems. So without this kind of cloud services, sometimes it's very hard, right? You do your research, I do my research. They have data. It's very hard to really put things together, right? To have a really big problem to focus on different aspects or different dimensions of real problem. But with AWS, that becomes easier. So overall, I think it's really valuable. And but I hope in the future, the services can be kind of cheaper for scientists, right? This way I can see the society will benefit more from the service.
Perfect. Thank you, Kun. It was very, very interesting and insightful discussion today.
Thank you so much for having me.
And that wraps up our fascinating conversation with Professor Kun Zhang on AWS for AI podcast. Professor Zhang's deep insights into causal AI and its applications across multiple domains truly demonstrates how this field is revolutionizing both artificial intelligence and scientific research. His work at the intersection of causality and machine learning opens up exciting possibilities for more interpretable, explainable, and robust AI systems. For those interested in learning more about Professor Zhang's groundbreaking research, you can find his publications and ongoing work through the Center of Integrative Artificial Intelligence at MBZUAI. If you enjoyed today's episode, please hit subscribe wherever you get your podcasts and leave us a rating and review. And as always, until next time, this is Hamza Mimi thanking you for listening. Keep exploring, keep innovating, and we'll catch you on our next episode.